That's a large picture. Oh, that's okay. Oh. So what I have here is a graph of a function. Right? That surface is a graph of a function. And the picture on the right is just zoom in of that surface, of exactly the same thing. Zoom in to that red point. You see red point? That's the point of my interest. It has coordinates x, y, and f of x, y. And if I'm interested in that point, well, thinking of that point as x0, y0, right? Then what you see there is that parallelogram in 3 space, and that parallelogram is right there. You see, practically these two are copies of each other. This is just zoom in, and well, we will look at more details of that zoom in later. So what is it that we are trying to do? Well, we are looking at this purple, or whatever it is, surface, right? And we are looking at that point, and we are trying to zoom in, and we know that as we zoom in, that surface becomes like a plane, and that parallelogram is supposed to represent that plane, that tangent plane. I never told you, it's called the tangent plane, the result of linearization, but you have probably guessed already. So now how to see the differentials there? Well, to see the differentials, you have to see the differentials of x and y first, because those are independent things, and those are the values sitting in the xy plane. So if I'm interested in this point xy, then in the xy plane, I'm going to change that by delta x in direction of x, and by delta y in direction of y. And that's what the geometry is of the differentials x and dx and dy. So this is dx, and that is dy. And those notations are shown there. So this horizontal segment has length dx, that horizontal segment has length dy. Now, what is the meaning of that parallelogram then, algebraically? Well, the meaning is the graph, actually, of the plane. So which plane? If you look at f of xy equals f of x0, y0, well, approximately equal, because we are taking linear approximation. I'm going back for a second to the Taylor series formula. So the value at any point is the value at our point of interest plus the partial at that point times change of x plus the partial with respect to y times change of y. So what you basically see here is that right-hand side represents a constant plus a linear equation, fx times a variable dx. Let me put it as x and dy as y, just in order to see the linear equation. Z equals linear of x and y, and that equation is exactly the equation of the tangent plane. It's just, instead of dx, you might think about x, but that's basically how you get the equation of tangent plane. Also, okay. Let's go back to geometry instead of staring at algebra. So what is it that we see about this parallelogram? So we see that if we go by dx in the x direction, then we know what the slope is in that direction of the graph. That's the partial derivative. And that slope is about the slope of that tangent line to the surface. So this purple line is tangent to the surface. And then that purple line gives the value of dx times its slope. And the value is right here. So if you go in the direction of x, your elevation will change by that amount. Then also, if you go in direction of y, your tangent line to that plane, right, will have a slope, and that slope is exactly the partial derivative, and that partial times dy times this change is going to be equal to the change of elevation as you go in direction of y. Now what happens if you put those two numbers together? Why is it that we algebraically add them up? Well, there is an observation we have to make here. So you see, I'm trying to compare that change in direction of x and that change in direction of y to the change in direction of dx plus dy. And what we see here is that if you put this change in direction of x and that change in direction of y together, they together make the total change of that tangent plane at this point of dx plus dy. So the tangent plane describes exactly how the change happens approximately if you make any step in any direction. If you go not only along x or along y, but in any place, you simply add up change in x plus change in y. And the sum is what you will see from tangent plane. So that's how you can see differentials dx, dy, and how they contribute to the values. Now, where is delta z? Well, delta z is, of course, the change of the value of the function, right? And that changes from all the way from here to there, to the point where the graph is. That's delta f. That's usually the thing we are interested in. But the approximation dz is going from that level of the original value only to the tangent plane. So that approximate equality, delta f approximately equals df, geometrically means exactly that. That this change is approximately equal to that change. And on this picture, it doesn't look like it. Right? So you see that this change, the actual change, is almost twice as much as the dz change. So the algebra may not be convincing unless you do what? Unless you decrease the values of dx and dy. And remember, everything happens locally. You always assume that dx and dy are small. Now, if you decrease them, what is it that you see? You see that the approximation dz is that large, and the actual value, delta z, is that large, and now the error is less than a third of the actual value. So you're making less error And if you decrease those again, then the error you're making is probably 10% of what you have. And if you decrease even more, then the error you make is almost negligible in comparison to what DZ is giving you. So that's exactly why you have to make those changes small. And of course, well, remember we tried to compute value of some function starting at 0. And then it took us thousands of steps of Taylor series to get close to the value. And the big difference is that if you start computation at a point closer, then you converge to the value much faster. And those dx and dy are responsible for the rate of convergence. Okay, so, well, all these are demonstrations on Blackboard. So you can look at them later if you want, play with them.